Well, thanks for that introduction, Don. It's always great to come up here and visit my friends and colleagues at GMRI. I'll be discussing something that's been a challenge for fishery scientists in the Gulf of Maine region for a while, and that is trying to manage the rebuilding of fisheries while the marine environment is changing so profoundly. I don't need to repeat the background, but essentially I'm on the applied side of science, where we're trying to collect data from the ecosystem and from our extractions, in this case the fisheries, to provide advice on how to manage the fisheries to try to achieve our societal objectives. So throughout all these organizations, we're really trying to apply our science towards the most sustainable use. Like many sciences, you don't do it on your own, and I'm really going to draw on the work from many of the collaborators that I have. Brian Rothschild was our founding dean in our program and really a pioneer in considering the climatic effects on fisheries. Kevin Stokesbury, who is department chair, has what we call an empirical approach. It's going out and getting the field data, and rather than relying on complex models, make our decisions based on data. Doug Butterworth from South Africa has really brought this from a global perspective of having very simple management procedures based on data and then applying advanced models to test their evaluation. The chief scientist here at GMRI, Andy Pershing, has made a very impactful study of climate change in the Gulf of Maine and its effect on drownfish. And Lisa Kerr, who Don just mentioned, who has been a great collaborator of mine for the last decade, working on the dynamics of populations and the effects of fishing and climate. Through this Marine Fisheries Institute, we've had several workshops, and one of them was explicitly on incorporating environmental change into stock assessment and management of fisheries. And a lot of the case studies I'll draw on are from the Transboundary Assessment Resources Committee. This is a partnership between Canadian and U.S. scientists. So I'll really drill down into examples like cod and yellowtail flounder. And then many in our department, the staff and students who work I will draw on. Finally, our region has a peer review process, which we all contribute to, which is the Northeast Regional Stock Assessment Workshop. So just a little bit of a roadmap of where I'll be going tonight is, first of all, just introducing fisheries from a very general sense and what we mean by sustainability in fisheries and how we go about the task of stock assessment. I'll give some examples of some success stories where our science has been able to affect positive changes in the fisheries that we're benefiting from now. And then I'll go into the not so good news, which is New England groundfish, where it's been a real challenge to rebuild groundfish in the context of climate change. A lot of what's happening in the environment is eroding the performance of our stock assessments. I'll throw out some possible solutions and try to support some general conclusions. I promise you that these are the only equations that I'll show all night. I spent a lot of my work in a computer in mathematical equations, but really they are just simplifications of the complex reality that's going on out in the Gulf of Maine. Essentially, the early years of our fishery science, we're trying to wrestle with the question of what is sustainability and what is overfishing and what is a sustainable yield. And it wasn't until Russell in the 1930s really conceived of the different components of population dynamics and productivity. And very simply, we have a stock biomass. This is an abundance of a given species of fish. Some of them survive and grow. Some of them produce new recruits of just eggs and larvae into the water column. And we harvest some of that biomass, and some of that biomass dies due to the natural causes, whether it's consumption or disease. Now, mathematically, that's expressed as the stock biomass at a given time has additions due to recruitment and growth of individuals, losses due to natural mortality, and losses due to our fishery yield. And that leads to the biomass in the next time step. So we can always derive biomass in any time as a function of the biomass previously, the additions and losses from natural processes, and our removals. So all we need to do is look at the difference from biomass at time t to t plus 1. We get a change in biomass. And the change in biomass are really from two sources. They're from the natural productivity, recruitment, growth, and survival, and our removals from yield. And so when Russell really just made the observation that if the natural productivity is greater than the yield, then the stock size will go up. So our yield is less than our productivity, we have sustainable yield. If the yield is greater than the natural productivity, we don't have sustainable yield, we drive the stock down. So a fairly early conception of population dynamics still stands as our definition of sustainable yield and overfishing. Now we realize that all of those productive rates, all of those components of production are a function of how many fish there are out in the population. So when we don't have many fish in the population, our stock biomass is low, we don't have much sustainable yield. We can't remove much because there aren't many fish in the population to grow and survive and produce new recruits. At the other extreme, when the stock size is near the carrying capacity of the environment, the fish are crowded in their habitat. They're competing for the same resources, whether it's shelter or food. So they're growing, they're so crowded, they're not growing as fast, they're not maturing as quickly, they're not producing as many babies, they may be dying in natural causes because of crowding and disease. So you really don't have much sustainable yield at those very high population sizes either. It's really at the intermediate stock sizes that we have the maximum productivity. There are enough animals in the population to be growing, to be surviving, and producing new recruits. There aren't so many fish in the population that they're crowding each other out. It's kind of a thinning the herd philosophy and theory here that the greatest sustainable yield is at intermediate stock size. And so we try to manage our fisheries for what we call maximum sustainable yield. Well, I'll give an example here from U.S. sea scallops, and it's a fairly typical story, at least in the early years, for many of our fisheries in the Northeast, is that around the 1990s, we had relatively low stock size. So the black line here is the stock size of the entire resource, and that's broken down into Georges Bank in the Mid-Atlantic. So recognizing that we had relatively low biomass, a management plan was established to rebuild that biomass to the stock size that could produce this maximum sustainable yield. We were much below that optimal level. And we needed to extrapolate what that maximum sustainable yield was. So we took models of growth rates and natural mortality and recruitment, and we had a model projection of what the stock size should be to produce maximum sustainable yield. It was far beyond anything we had observed since we started surveying this population and monitoring the fishery. The model that we used, again, predicts that when we don't have any fishing mortality, we're going to have the maximum biomass. And this makes sense. This is an unfished population. We expect this to be near the carrying capacity of the habitat. But as we start fishing harder and harder, that biomass should come down, but our yield should come up. And we should reach an optimum yield when there's enough stock size out there, but we could fish too much so that we start losing yield because we have so few fish in the population. So this is how we determine maximum sustainable yield. The fishing mortality associated with maximum sustainable yield, and the biomass. This is the stock size associated with maximum sustainable yield. So for scallops, this is the biomass that we think we need to rebuild to achieve these maximum sustainable yield objectives. So when we fast forward with scallops, not only did we achieve the stock size that produces maximum sustainable yield, we exceeded it. And the U.S. sea scallop fishery now is about a $600 million a year fishery. The fishermen sacrificed early on in the management plan when they had to reduce their fishing effort, reduce their catches, are now benefiting from those sacrifices. And this is a success story, both in science, the scientific expectations were generally true, and also societally, that we're getting the objectives out of this fishery that we want. When we look back at the model that we used to determine that rebuilding target, the actual trajectory didn't follow that model exactly, but generally it did. That over time, as we reduced the fishing mortality, we got increases in biomass so that we're actually able to exceed our targets for maximum sustainable yield. So now I'm going to go into groundfish. And these are surveys of all 19 groundfish stocks that we have in New England. And when you look at them in aggregate, they actually look a lot like the scallops story. We had some early high biomasses, but those were depleted largely because of excessive fishing. We started a management plan. We started closing areas, reducing the days at sea, increasing the mesh sizes, and the groundfish resource recovered. And it has been fairly high, about the size it was pre-collapse, until you start looking at the colors. Because what's driving this are haddock and redfish. In fact, in the last year, so we just did these assessments about last September, most of the groundfish biomass are the two haddock stocks, pollock and redfish. And there are other stocks in the groundfish complex, like cod and yellowtail flounder, that are a small portion of the total biomass. So for some stocks, they responded similar to the way scallops did, similar to the way the models expected, is that if we cut back on fishing, the natural productivity will allow the stock to rebuild, and they can achieve maximum sustainable yield. Cod and yellowtail flounder used to be two of our three principal groundfish stocks, together with haddock. But two of our principal groundfish stocks did not respond the way we expected. And in simple terms, the reason that the models that we used to project this didn't work is that we did most of our learning about productivity in times when the fishery was not strictly managed, when we had relatively high fishing mortalities producing relatively low stock sizes. And so from a model building perspective, we need to simplify all the complexities that are happening out in the marine ecosystem, and really all we need to do is monitor the primary predator, and that is the fishery. So if we can monitor the landings for the fishery, the amount that they discard at sea, and we are accounting for those removals in our model, then we're really getting a good sense for the population dynamics. But because of our successes in ending overfishing, we're now fishing at a much lower fishing mortality rate, and we have much higher stock sizes. So we have more scallops, we have more haddock, we have more redfish and pollock. And so now, when I go back to my model building, the fishery is not necessarily the primary predator anymore. We're removing less from the system, and there are many more predators in the system, and so the models that have helped us end overfishing are now not performing so well, because in addition to monitoring the landings and the discards from the fishery, we need to monitor the consumption of other fish, we need to monitor the environment for the environmental effects, and so really the ecosystem is having much greater effects on the populations now than they did when we were fishing very hard. So the first case study I'll go down into with groundfish is Gulf of Maine cod. Back in about 2008, we did a stock assessment that suggested we had about 20,000 tons of spawning biomass in cod. And it was well on its way to recovery. So this trajectory looks a lot like that scallop and haddock recovery. Unfortunately, when we updated the assessment, those estimates were revised downward. This is what we call a retrospective pattern. In retrospect, these were bad overestimates of the stock size. And they led to management decisions that allowed too much fishing. And so that continued to drive the stock down. So it was this retrospective error that was causing what in retrospect allowed too much fishing. Now what we were able to do was to go out and tag cod. In fact, Gulf of Maine Research Institute was the lead organization in tagging cod for this study. And we were able to find that natural mortality actually had increased. So part of the reason for this retrospective inconsistency was we were assuming a relatively low and constant natural mortality rate. When we allowed that natural mortality to increase, the retrospective inconsistency went down quite a bit. And so we really resolved something here for Gulf of Maine cod, that when we assumed a constant environment, in this case natural mortality rate, the models were not performing well, at least in terms of consistency. And when we allow the natural mortality rate to increase, it improves the consistency of the assessment quite a bit. It doesn't improve the estimates. I mean, we're not creating a lot more cod, but we're at least explaining why we've had such a decrease in cod. So we have changes in natural mortality rate. Beyond just monitoring the fishery, we can tag fish and see what our recapture rates are. For the herring stock assessment, we can monitor the stomachs of predators and how much they're consuming, and we can try to get time-varying estimates of natural mortality. And so that helps us in our definition of sustainability. Because remember, sustainability is taking less yield than the population can produce. And natural mortality and survival are a big part of that. So assuming that natural mortality has increased, has removed a lot of these retrospective patterns from stock assessment. But it also poses another challenge. What do we expect for the future? In the scallop example, we were making projections about the future, about how much we wanted to rebuild the stock to get maximum sustainable yield. Do we assume that natural mortality is going to stay high, or do we assume that it's going to come back down to what it used to be? And I'm going to leave these with question marks because right now this is a hotly debated issue that we have in New England. Since those assessments, we've updated the cod assessment. We're now removing less cod from the system than we have since colonial or pre-colonial days. We started monitoring cod landings in the late 1800s, and they were orders of magnitude higher than what we're taking out now. And this was from emergency actions, closed areas, no possession for recreational fishermen. Fishermen are actively avoiding cod. We're catching less cod than we have in at least the recorded history. Despite that, the spawning stock biomass continues to go down. We still have low biomass. We don't get the positive increases we would expect from our theory. Right? If we remove the yield, then the natural productivity should allow the stock to grow, but we're still missing something here. We're still missing that the productivity of cod has decreased to much less than what it used to be. And the people at GMRI have really started shedding light on what we're missing. Andy Pershing and his colleagues had just published a paper that came out in Science that identified our region as one of the worst regions when it comes to the rate of warming of sea surface temperatures. So their analysis looked at sea surface temperature from throughout the globe. In some areas, it's actually cooling. In other areas, it's warming. In our area, we had warming at a rate faster than 99% of the rest of the world. Basically, we're warming at a higher rate than the rest of the world. And that's having effects on our fish population. This is from the same paper that Andy published. We saw that the spawning stock biomass was going down, and recruitment is also going down. And when we account for temperature, we can explain that decrease in recruitment much better. At higher temperatures, cod are producing many fewer recruits. So those are the young fish that are the new members of the population. The recruitment component of production has gone down greatly in the Gulf of Maine due to warming. There's also been more mortality. As the temperature goes up, the mortality rate goes up. So two components of production, recruitment and mortality, are being negatively affected by the warming that we've seen. If we go further north, we actually see the opposite effect. The very same week that Andy and Lisa and their colleagues came out with their paper in Science, this paper came out in one of our scientific journals that showed that cod off Newfoundland and Labrador are actually benefiting from the increase in temperature. So they've seen an increase in temperature over the last 20, 30 years. And the trajectory of cod initially looks a lot like our New England stocks. And actually, there were a lot of the same distant water fleets that caused the initial decline. So in the mid-90s, just like scallops and haddock and yellowtail flounder off our waters, cod off of Newfoundland were at fairly low biomass levels. And they stayed at low biomass levels for about 20 years, despite a moratorium on fishing. So those fishery scientists and managers we're doing exactly what we're doing now with Gulf of Maine cod. We backed off fishing almost entirely. They had a moratorium on fishing cod, and for 20 years, that moratorium did nothing. It wasn't until the water started warming, some of the prey, capelin is a small pelagic fish that cod feed on. When capelin started returning because of higher temperatures, the cod started rebuilding to almost pre-collapse levels. So we have a warming condition that's negatively affecting cod in the Gulf of Maine, positively affecting cod up off Newfoundland. Going back on our science, we've typically viewed climate variability in the science of trying to predict recruitment. What environmental conditions produce a really good year class of fish or really bad year class of fish? And one of my mentors, Brian Rothschild, was a pioneer in that evaluation of fishing in the context of the environment. But since then, we've gone from climate variability to climate change. And we really have been faced with profound changes due to the environment. Here's a distribution of red hake that used to be distributed down off the mid-Atlantic, down towards Maryland and Virginia. But in the last decade, we don't see any red hake down there. I could have easily put black sea bass up here, where black sea bass used to be all down in the mid-Atlantic, and now we're catching them up in the Gulf of Maine. So as a response to the warming, we've had geographic shifts. We've also seen that, similar to the northern cod, the species that prefer warm water are producing more and more of our global catch than the cold water species. So what we're seeing in New England is being reflected throughout the world. So what can we do with this? I'll offer three general approaches to how we can manage rebuilding in the context of climate change. The first is to try to understand how the environment is affecting those components of productivity. How is it affecting survival? How is it affecting recruitment? And how is it affecting growth? And so if we go back to all of our components of productivity, we have some sense of how warming or salinity or circulation are affecting all of these processes. The second general approach is we can go away from our single species population dynamics and start looking at the ecosystem as a whole. We can start looking at the energetics of how much plankton are being produced, how many plankton are grazing that primary productivity, how many secondary feeders are feeding on those plankton, how much of that is getting into our fishery resources. In looking at the marine ecosystem as a system, we can more explicitly account for the climate change. The third way is to simply go back to the data. Go away from the dynamic models that give us expectations of productivity and go back to the data that we're collecting to make decisions based purely on the data that we have rather than model results. So I'll go into the first example, and that is accounting for climate effects in our components of production. Here's another Gulf of Maine resource, pandalid shrimp, that are very sensitive to the temperature. And we've seen in the last decade with warming, we get many fewer recruits as a function of the spawning stock. That back in the 80s, when we had relatively cold environments, we were getting a lot more baby shrimp from the spawning stock that we had. But as the temperature increased, we're getting less and less recruits as a function of the stock size. And if we fish this shrimp stock at a given fishing mortality, we're going to reach an equilibrium line where at a given fishing mortality rate, we're going to maintain a fairly healthy stock. We're going to produce a lot of recruits. As the temperature warms, that same fishing mortality now is producing much less stock and recruits. And when it gets even warmer, we're getting less. And that's why the Gulf of Maine shrimp fishery was just closed again for next year. So the moratorium that's been for several years now has been extended to next year because the water is so warm that the population is not producing enough recruits to be sustainable. We can look at the other components of production. This is a stock assessment of Atlantic menhaden, which is a forage species. We can monitor the consumption of menhaden by these three predators: weakfish, striped bass, and bluefish. We can account for the recovery of striped bass and their consumption on menhaden. And rather than just assuming a constant natural mortality rate, we can now have a time-varying natural mortality rate that responds to the consumption by different predators. So we saw with shrimp that we can incorporate temperature into the recruitment expectations. We can incorporate predation into our mortality expectations. We can start to do this, but it really requires a lot more data. In addition to monitoring the fishery, we now need to monitor the stomachs of the predators as well. So this becomes a scientific challenge to understand the mechanisms and to get the data we need to do this. Ecosystem scientists would say that as we try to do that for all the species of interest in our system, we don't have the budgets to collect all that data, and our models would become overly complex so that we really don't understand them anymore. And really, we've got to let some things go. And ecosystem theory is really just a subset of systems theory, where the whole is much more important than the sum of the parts. Is that if we start modeling the entire ecosystem and how it responds to climate and how the productivity of the fishery resources respond to climate, we'll have a much more tractable system that we can manage and we can monitor. There are two challenges with the science and one challenge with the governance. We need to define boundaries. So here we have our Northeast U.S. large marine ecosystem. Of course, there's no closed boundary with Cape Hatteras. We have marine mammals and large pelagics that are swimming into the region each season. So it's difficult to draw the boundaries to model these ecosystems. We now need to monitor, in addition to our fishery resources, the benthos, what's going on down at the bottom, what's going on in the plankton. But really, societally, we need to confront trade-offs. Do we want to have all of our species producing maximum sustainable yield? In addition to cod and haddock, there's dogfish. There's fish that are not economically important to us. Do we want to protect marine mammals as a priority, even if they are preying on some of our valuable groundfish? So these trade-offs really haven't been confronted to really implement ecosystem-based fisheries management. So I'll go to kind of a fallback position, and that is if we don't yet have the science to understand the mechanisms of climate effects on single species productivity, we don't yet have the governance or have made the trade-off decisions to have a full ecosystem approach to fisheries, what I'll suggest is that until we have that, we should fall back on an empirical approach to managing. And the last case study that I'll talk about is yellowtail flounder on Georges Bank. And I'll go back to 2004 when we published a paper, The Collapse and Recovery of Yellowtail Flounder on Georges Bank. We had two very different models of our fishery data and our survey data that showed the decline, temporary increase, very low stock levels in the late 80s, early 90s, and a rapid recovery after we started cutting back on fishing. Unfortunately, after we published that paper, the very next year we updated the assessment, and the models that used to agree with each other now are disagreeing with each other greatly. Whether it's an aggregate age model, an age-based model, it's very different results. And the reason is the same problem that we saw with cod, but we have this retrospective pattern, is that when we did the stock assessment back in 2000, we thought there were about 45,000 tons of yellowtail. The very next year we updated that came down, and it came down again. So that now, if we go back to our updated estimates, it's less than 10,000 tons. So about 20% of what we used to think there were out there. And of course, when this estimate was given to the fisheries managers, they thought that they could sustainably take a large portion of that, and in retrospect, they took too many yellowtail. So when scientists are given this information, they'll do whatever they can do to try to fix it. And one of the attempts at fixing it was what we call the split series. We basically took the long time series of surveys that we have that had the same vessel, the same net, the same protocol, and we assumed that the catchability, the efficiency of that survey changed in 1995. We really didn't have any empirical evidence for it, but we assumed it's changed, and when we did, the retrospective pattern went away. Kind of similar to what I showed for cod, where when we assumed natural mortality was constant, we had a retrospective pattern. When we allowed natural mortality to increase, the retrospective pattern went away. It looked like splitting the survey fixed the problem here. Unfortunately, it really gave us, when we started looking at the other results from the model, it implied that the catchability of the survey went to greater than 100% after 1995. That before 1995, as a function of age, the efficiency of the net was about 20%, which makes sense. When you take a survey net and tow it over the bottom, you don't catch all the fish in the path of the net. You certainly don't catch more than 100%. So even though we removed the retrospective pattern, it really was creating other problems. When we look at the data itself rather than the model, we had high survey catches. The circles here are 3 different surveys: the U.S. fall, U.S. spring, and the Canadian survey. We caught a lot of fish. We didn't catch many fish at all in the late 80s, early 90s. Then we started catching more fish in the surveys. When we look at the model used to give us much greater stock size than indicated by the surveys, and that made sense because we're assuming 100% efficiency here. We know that the survey is not 100% efficient, so the model was giving us more stock size in the surveys. However, that went the other way. After we allowed for the efficiency to change, we're now seeing many years where our survey estimates of stock size are greater than our model estimates. It's really not making sense when it comes to looking back at the surveys and the models. So we took this to an international level a couple of years ago. The International Council for the Exploration of the Sea took this case study as a challenge, and modelers from all over the world took the same data and they plugged it into their favorite models, and some models were getting estimates of very high stock size, other models were getting very low stock size. Really a great deal of scientific uncertainty. We cannot reconcile what's going on with Georgia Bank yellowtail flounder. Soon after that analysis, the model that had this fix of reducing the retrospective pattern was no longer a fix because the retrospective pattern came back. So I had ended at 2005 in my last plots. These are since 2005. We now have still about an 80% reduction in our estimates of stock size. But now we really start going down the rabbit hole, is that not knowing what to do with this, we don't know if it's natural mortality, decreased recruitment, change in survey efficiency. We don't know what's driving this inconsistency. We don't know what's wrong with the model. And so the response was to correct for the model results. We take our last year of stock size estimate and we adjusted downward for the amount we've been off in the past. Unfortunately, it's correcting it further away from the survey data. Remember, the survey data were low, but they were greater than the assessment. We're now adjusting it further from the data. So, of course, this isn't what the fishermen saw in the water. They said there aren't as many yellowtail as there used to be, but it's hard to avoid yellowtail flounder. We're seeing yellowtail flounder wherever we go. So really what we've got into is that we started believing the model more than we should. We say that all models are wrong, but some of them are useful. We can learn from our models, but we can't believe that they're true. We need to accept that they're simplifications of a complex reality, and we can learn the most when we have intermediate belief in the model. When we completely believe the model, we're really not learning anything, and we really don't learn anything if we don't try modeling our data. So we went out to the field. We started doing some dredge surveys and tagging studies. So if we compare now the model estimates, so this is the age-based model estimate of biomass. This is the same model's estimate of spawning biomass. And here's the retrospective adjustment. Remember, we don't just take the best estimate from the model, we adjust it downward to account for that retrospective pattern. We went out and did a lot of independent studies. We did a Peterson experiment in a small enclosed area. We had some dredge surveys. We had cooperative surveys with fishermen. And even though these estimates were from a small portion of Georges Bank, all of them were either greater or equivalent to the entire bank estimate of stock size. So we had independent information to show that the model was really going wrong and the adjustment was in the wrong direction. We were able to revise the model. We now assumed a higher natural mortality rate. It started being much more consistent with our independent field observations. But we realized in total that the model was not informing management the way it was intended to. So the model was rejected, and now we are using our survey estimates of biomass to manage this species. And this was a precedent in our region. In fact, it's one that was repeated just earlier this year for Georges Bank cod. Georges Bank cod had the same problem, in which if we had a retrospective pattern, we had about a 240% problem here, where our red estimate here was about 240% of what we now think it was. So in retrospect, our stock assessments were badly optimistic. The resulting management decisions allowed too much catch, and it kept driving the Georges Bank cod stock further and further down. And when we put this retrospective correction on, so again, not just taking the best estimate from the model, but correcting it downward to account for these, when we did that and projected it forward, we realized that our fishery that's actively trying to avoid cod and catch things like haddock had already caught more cod, and that was back in September, than we thought there were in the population. So we had a real honesty check here that our model was going in the wrong direction. We had real data that showed the model was wrong. And so we rejected the model just like yellowtail flounder, and we're really just now managing the stock based on the data, based on the survey trends and the catch that produced those survey trends. So finally, there is one step that we need to take. We can manage our fisheries and we can assess the health of the stock just based on data. And whether that's survey trends, catch unit effort from our fisheries, the size structure. But what we need to do is evaluate how this data-based management meets our objectives. So what we can do is to try to devise a management procedure. And conventionally, this had a stock assessment that was an age-based stock assessment based on monitoring our fishery removals and our surveys, an elaborate model that led into a maximum sustainable yield harvest policy. We can simplify that management procedure. Maybe the stock assessment is simply a survey of the resource. And maybe the harvest policy is you just adjust last year's catch up or down based on whether the survey is going up or down. So a very simple management procedure. But what we need to do is take everything we know about this fishery resource, all of those components of production, the growth, the natural mortality, the recruitment, and maybe we have different scenarios. Maybe we have different environments. Maybe we have a high natural mortality scenario and a low natural mortality scenario. We simulate a fishery. We know what our fleet size is, what the selectivity of that fleet is, what ages and sizes they catch. It's that we're going to call an operating model. And this exists in a computer. This has everything we know, all the research we've done about the species, about the fishing gear, and we have an operating model that's as complex as our stock assessment model used to be. From that, we generate the typical data that we collect. We have surveys, and they may be imprecise, they may have some signals, but they also have noise. We monitor the landings from the fishery. We also monitor the discards, and maybe the discards are not well estimated, or maybe they're underestimated. But we have our perceptions of what's going on in reality, and we feed that into stock assessment. And if this is a survey trend, and we need to adjust the catch downward because of the survey trend, that feeds back onto the fishery. And so now, if we have another time step in our computer model, we now reduce the amount that we're taking out of the fishery resource, and we collect another year of data. And we keep repeating that loop over and over and over in the computer so that we can see how our virtual reality responds to our management procedure. And from this, we start to see, do we collapse the population with this simple database management? Do we get somewhere close to the maximum sustainable yield? And we can manipulate our assessment and harvest policy. We can have alternative management procedures that meet the outcomes that we expect them to through this systems analysis. And so with that, I'll close, is that we need to accept that the environment has changed profoundly off New England. Our fish populations are changing as a result of that, and we expect these changes to continue. All of the climate models say that the trends that we've experienced in the last decade are only going to continue. Unfortunately, the conventions that we've built in stock assessment science, the ones that have really informed the recovery of many stocks, are now eroding because they all assume a constant environment. And that used to be a fair assumption because the environment was changing up and down, but there really was no trend until the last 30 years. And so now that we have climate change, we can no longer assume a constant environment. And because of the change, the performance of our conventional stock assessment models is deteriorating. And so where we need to make decisions today, we can't wait for the science of tomorrow, is that we need to inform next year's fishery and what is sustainable yield. So we can't wait to develop more complex models that have the environment driving recruitment or mortality. We can't wait until we've made some of these critical ecosystem trade-off decisions. While we need to make decisions, we need to fall back to the data. These empirical methods of going out in the field, estimating the stock size or the relative stock size, the trend in stock size. Sustainable catch. This could be a proportion of last year's catch. If last year's catch drove the stock down, we need to cut back the catch. If last year's catch allowed the stock to double, maybe we could take a little more. A robust approach, and we need to test the performance of that in silica so that hopefully it performs well out in reality. Thank you very much.